All right, so applications of exponential functions. The models, word problems that we're going to be looking at, they all have the same formula or model. Okay, so whenever you have an exponential function, you will always be in the form y equals ab to the x. So what does that mean? Well, that means that with an exponential function, we always start with a value. So the starting value, we designate the letter a, and then we always take that starting value and multiply it by a common ratio. So that is our b. And then x is how many times we're going to do that. So all exponential models are exactly the same. You start with a number, you multiply it by a common ratio, and you do it a certain number of times. The difference in the base is going to determine whether it's growth or decay. So growth meaning that it's going to be an increasing function, and decay meaning it's going to be a decreasing function. Right? It's either going to go up or down. So if b is greater than 1, right? So sometimes you'll see it like this. If b is greater than 1, it's going to be a growth function, meaning it's going to get bigger. If b is between 0 and 1, meaning a fraction or a decimal, then it is going to be a decay function, meaning it's going to decrease, it's going to go down. So we don't talk about negatives because negatives do different things. So a negative, we're not going to say if b is less than 1, because if b is a negative value, it's going to be a reflection, which is not the same thing. So we'll either say it's either a whole number or it's a fraction or decimal. Okay? So, for example, here are some graphs. So the graph on the right is base 2. Right? So it is, I've got a table of values here. We put in some numbers for x, and we determined our values for y. And we've looked at these graphs earlier, right, in an earlier unit. So you'll notice that b is a whole number greater than 1. Okay? The a here is actually 1. We just don't have to write it. It's actually 1 times 2 to the x, but we don't really need the 1. Whereas the graph below is base 1/2 to the x. And you'll notice that that is a decreasing function. So if the base is a fraction or a decimal, it will be a decay or decreasing function. If the base, the common ratio, is a positive number, it'll be a growth equation or an increasing function. So sometimes they will ask you to match the equation with the graph. So you know if it's going up, it's got to be a base that's a whole number bigger than 1. And if the base is if the graph is going down, you know that the base needs to be a fraction or a decimal. You might get it with an equation. So this is a typical question. Determine whether each function represents growth or decay. All we're looking at is the base or the common ratio b. That's all we're looking at. We're not looking at a, the starting value. We're just looking at b. So here, the first one, b, so a is 4. That's the starting amount. B is 0.8. Since 0.8 is a decimal between 0 and 1, it would be a decay function or a decreasing function. In question B, the starting amount is 2, and then the common ratio is 5.7. Well, 5.7 is greater than 1, so that would be a growth function. Okay. Question C, so don't get confused, the a value is a fraction, but we're not looking at the a value, we're looking at the b value. So don't get misled that the fraction is in there. The fraction is just a starting amount. The 5 is the common ratio, and that is a value greater than 1, so that is growth. Don't get distracted by negative values for a. A is -2, that's the starting amount, but that's not what we're looking at. We're looking at b, which is the value in the bracket. The common ratio, it's greater than 1, so it is growth. Okay. Question E, we have a common ratio of 3 over 5. Well, 3 over 5 is a fraction that is in between 0 and 1, right? It's less than 1 but greater than 0. So that would be decay. And then finally, the last one, the common ratio is 3. That is growth. The negative in the front is something completely different. If the base is greater than 1, it's going to be growth. So that's another common question. It might say, here's a graph or here's an equation. Identify whether it's growth or decay. Here's another question with graphs. You want to match the situation with the graph. So when I read through these 4 scenarios, A is a population that doubles. So that means it's increasing. B is the value of a computer, and it says right there it's decreasing. C is money that's earning interest, so it's increasing. And D says it decays, so that is decreasing. So the first thing I would probably do is identify which ones are going to be going up and which ones are going to be going down. So increasing A and C would be the 2 graphs that are going up, so it's either A or D. And then I'm going to try to determine which is which. So the first one doubles. Okay, so the common base would be 2. And then the last graph is much steeper. So C has a interest rate of 11%, and A is a population that doubles every hour. Okay, so I have to kind of look at which one would go with which one would be steeper. Well, the 11% is a bigger interest, a bigger growth factor than 2. Okay, so I would say that this one is scenario C, and this one is scenario A. Mainly because graph D is steeper, and the growth factor is much higher at 11% than at 2. Okay, B and C. So B decreases by 18% and D decreases by 5.5%. So B decreases more, right? 18% is a steeper decrease than 5.5. So I would say this is graph B and this is graph for situation D. So the first thing you want to do is distinguish which ones go up, which ones go down, and then look at the steepness of the graphs and see which one is changing the most. All right, so those are equations and graphs. So now you're going to get some scenarios. So you want to be able to determine an equation for these scenarios. They'll always ask you for the exponential model, which is really just a general equation for that scenario, and then you're going to use that equation to answer some sort of question. Okay, so population is a common question with exponential. Its population is always going up or going down. So it says we have a starting population of 25,000 people. So we know that. So we know the model is going to be a b to the power x. So we know the starting amount is 25,000. It is increasing by 5.5%. So when you are looking at the common ratio, and it is given as a percent increase or decrease, remember that you are always starting with 100%. Okay, so I'm going to use P for population. My starting population is 25,000. 100% means no change, right? If I have 100% of something, I have the exact same amount. So I'm going to either add to the 100% or I'm going to subtract from the 100%. So this says it increases by 5.5%. So I'm going to add 5.5% to the 100. And that gives me 105.5%. And then I'm going to change that to a decimal by dividing by 100. So it'll be 1.055. That is my common ratio. So it is worth the effort to write it out, because a lot of times the error made is always the common ratio, the decimal. Sometimes I would get 5.5 in that bracket. Sometimes I would get 0.055. Forget about the 1. So remember, it's always starting with 100. It's either going up or it's going down. And then t is how many times we're going to do that, the number of years. So this is my exponential model. And then we're going to answer the question in B, what would be the population after 8 years? So once we have the equation, we can just put in a value of 8 in for t. And then it's just a matter of typing that into our calculator. Remember that you always want to do order of operations, which is exponents first. So we'll do to the power 8 first. And then we'll multiply that by 25,000. And I'm probably going to round to the nearest whole number because it is the number of people. And I can't really have decimal 2 of a person, so I'm just going to round to the nearest whole number. Okay, so that's a typical exponential question with population. Okay, this is another population. So it's starting with 8,000 people. This time it is going down by 2%. So we'll start with the same model, y equals a times b to the power x, p for population. Starting population is 8,000. And then b starts with 100%, and this time we are going down by 2%, so we're going to subtract 2% from the 100, which gives us 98%. As a decimal, that would be 0.98. So that means next year I would have 98% of the population that I had the previous year, right? So we don't put in 2 here, right? Don't be tempted to put in 2%. It's the amount that's left over, which would be 98%. So it is worth the effort to do this on the side with the 100%, just to make sure that you get the right number. And then in part B, it wants us to find the population after 5 years. So we already have the model. We'll just put in 5 for t. And we get approximately 7231. Okay, so those are 2 examples of where the population is going up or the population is going down. Either add to 100% or subtract from 100%. Okay. Another popular model is compound interest, which you've probably already seen several times. We do it in grade 11 for sure. But we'll review it again. So with compound interest, the model is given here. It's still an exponential model, right? It's just that we use different letters. So instead of y, we use a, which is the final amount. Instead of a for starting value, we use p for principal. So principal is my starting amount. And b is always 1 plus I. 1 is representing 100% plus the interest rate. Okay, so that's what that 1 is representing, 100% plus the interest rate. The only thing you have to remember with compound interest is the I needs to be divided by the number of compounding periods. Right, that is important to remember that. So we'll look at that in just a second. So I is always interest rate divided by compounding periods. So is it annually? Is it quarterly? Is it semi-annually? Is it monthly? N, or T, is the total number of compounding periods. So in this question, we've got A, the starting amount is $500. 1 plus the interest rate is 6%. So as a decimal, that would be 0.06. You have to remember that it's divided by how often it's compounded. So it's compounded semi-annually, which means twice a year. So that means that 6% is going to be divided in 2. So you're going to get 6% by the end of the year, but if you get it twice, they're going to break it up, and you're going to get 3% each time, so that by the end of the year, you get your 6%. The total number of compounding periods is twice a year for 4 years. Okay, so N is semi-annually times 4 years. So N is twice a year for 4 years, which is 8. So the most important things with compound interest is the I and the N. So it's going to be 1.03, right? 0.06 divided by 2. And then 2 times 4 is 8. All right, so let's see how much that is. So we end up with $633. I'll do dollars and cents, and 39 cents. So that means that we earned $133.39 in interest over that period of time. Okay, the 500 that we started with, take that away from the total, and that's telling you how much interest you earned. Let's say it was compounded monthly. What if the amount, let's just put 500 here. What if that $500 investment was compounded monthly? How does that change the equation and the answer? So we still got A, we still start with $500. 1 plus the interest rate is still 6%, but it is going to be compounded monthly, so it will be divided by 12 instead of 2. And the total number of compounding periods will be monthly, so 12 times a year for 4 years. Okay, so let's see how that changes our results. So think about this. We have the same amount of money invested at the same interest rate at the same number of years. The only change is we're compounding it monthly instead of semi-annually. So this is going to be 1.005 and to the power of 48. And works out to be $635.24. So the idea of compound interest is that the more often you compound it, so here we have the same amount of money over the same time period at the same interest rate, but we earned a bit more money, right? A couple of dollars more by compounding it monthly instead of semi-annually. So the more often you compound, the more money that you make. Okay, and you probably already knew that because you've done compound interest before. But the idea is compound, especially with exponential functions, the more often we apply the exponent, the more money we're going to make at the end of the day. Okay. So for those of you who arrived a little late, with the MAP students, we'll do some more applications next lesson, but looking at the models, all the models are a times b to the x. We've looked at graphs, right? If the base is greater than 1, the graph will go up. If the base is less than 1, but greater than 0, it will go down. If you have an equation, you're just looking at the b. You're not worrying about the starting amount, you're just looking at the common ratio. If it's less than 1, it'll go down or decay. If it's greater than 1, it'll go up. Okay? Likewise with graphs, and then you have your exponential models here. Okay? I'm just going to mute for 1 second while I do the attendance. Okay, are there any questions on the work that we have done so far or anything related to midterms? Okay, midterms, last day for work submission is the 9th, which is next Monday. So a week today. You've got 1 week to complete your tasks and any strand tests. Is there any questions on what's expected for midterms? Okay, so Spencer has a question. 3 consecutive odd numbers whose product is 12. So just let me bring up the whiteboard. So if they are 3 consecutive, so 1287, okay. So if it is 3 consecutive odd numbers, so 3 consecutive odd numbers would, for example, be 9, 11, 13. Those are 3 consecutive odd numbers. So if the first one is x, the second one would be 2 more. Right? So 9, 11, 13. Every consecutive odd number is always 2 more, so the next one would be 4 more. So their product is 1287. Right, so that's what you're going to get. So the first number would be x, the next consecutive odd number would be 2 more, and then the next consecutive odd number would be 4 more, and then we would expand. Right, so let's multiply the first bracket. We want to put it in standard form, so I'm going to multiply x by x plus 2. And then I'll multiply this bracket. So what I want to do is get an equation. So we'd get x3 plus 4x squared plus 2x squared plus 8x. Sorry, it's a little messy. It's hard to write with the mouse. And then since we want to solve, it has to be in standard form, so we need everything on the left equal to 0. So I'm going to add the 4 and the 2 is 6x squared plus 8x, and then bring over the 1287. And the reason they say use a calculator is probably because you can't factor it. So you could type it into Desmos. Don't worry about a graphing calculator. Just type it into Desmos and see where the graph touches or crosses the x-axis, and those will be your value for x. So let me see if I can just type it in here. So you're not going to get any questions that you'll have to use graphing software. You'll be getting questions that you can, that you're able to graph. So I'm just going to type this in. I'll show you what the graph looks like. Let's see, plus 8x. Okay. So I'm just going to switch screens for a minute. Okay, so if you can see this screen, I've typed in the equation, and you'll see that it crosses the x-axis right here at 9. Okay, the rest of the graph you can't see, but the other parts of the graph are not going to be visible. Right, so there's only one solution, so my answer is 9. I can see that from Desmos. And so the 3 numbers would be 9, 11, and 13. Okay? But if you're going to get questions, and then if it's 9, you might be able to factor some of that, but in general, if you're going to get a question like that, you'll be able to factor it. So we would find a root, right? We would find a 0, then we could do our long division or synthetic and find those solutions. And you could also check your answer. Right? We could say, okay, the first number is 9, that means the next one's 11, and the next one's 13. So 9 times 11 times 13 is 1287.